In this video, I want to talk about how to distinguish between SN2, E2, SN1, and E1. If you're taking an organic chemistry test and you have to identify the best reaction mechanism, it might be a little daunting because there's so many different options. Well, this video is made to break down exactly how to approach these problems and how to make the best prediction. So I want to start looking here in the middle. I think that the nucleophile is going to be your best measure of which to use. So the first thing you want to look at is, are you working with a strong or a weak base? Well, what does that even mean? You want to look at the conjugate acid. That means you want to look at the base, look at your attacker, and give it an extra proton, because that's what a base is, a molecule that accepts a proton, a hydrogen. If you look at that conjugate acid, try to determine if it's much more stable or if its stability didn't really change too much. An example of these can be looking at hydroxide. If you have a hydroxide, it is an anion. Anion means it has a negative charge. If we want to be neutral, we need to get rid of that negative charge. We need to add a positive charge. That comes from the proton. So any anion that you see is going to be a strong base because it will want to neutralize, so it will want that proton. If you see something like NH3 and you look at the conjugate acid, which is NH4+, that's not really as stable as NH3. So if it were to gain a proton, that wouldn't be ideal. Its conjugate acid would be strong, meaning that it would want to give that proton back. It doesn't want the proton. That means it's a strong conjugate acid, but the base is weak because it's stable as is. You want to look first to see if it's a strong or weak base. If it's a strong base, you're most likely going to go through E2. E2 mechanisms like strong bases because they just take one of the protons and that's it. They form the double bond. The next thing you want to look for is if it's a strong or weak nucleophile. All of our attackers are going to be bases. They're all going to be nucleophiles, but you want to see if it's a strong base or a strong nucleophile. Well, a nucleophile is basically anything that has lone pairs is a nucleophile. It has extra electrons. The thing is, how bad does it want to share those electrons? Well, if it has a negative charge, again, we want to have the lowest energy, we want to be neutral. The first thing you want to look at is going to be the charge. If we have a negative charge, that's going to be a strong nucleophile or an indicator of a strong nucleophile because it wants to give those negative charges away to become neutral. The next thing you want to do is look at crowding or steric hindrance. So you want to see how big is this nucleophile. If it's very large, it might be more willing to become a base and just take a proton rather than going through all the substituted groups and attacking. If it's a smaller molecule, it's going to be a stronger nucleophile. If it's larger, think tert butoxide. That's very large. We have a tert butyl group and then our oxygen. That's very large. It's very difficult for that to do a backside attack if we have any sort of substituted groups on our carbon with the leaving group. If we're smaller, we can zip through all those areas of electron density and avoid all that steric hindrance. That's what would make it a strong nucleophile. The other thing that you want to see, and this is sort of associated with the charge, is the resonance. You want to see if those electrons, that negative charge, if it's localized or delocalized. If it's delocalized, then it's going to be a weaker nucleophile because it's not as worried about that negative charge because it could just distribute it throughout the molecule with its resonance structures. Whereas if it's localized in one spot, that's going to be an area of high electron density. That's going to cause more energy, which the molecule doesn't want to have. It wants to be at its lowest energy, so you want to look for resonance as well. More resonance means less willing to want to give away those electrons. Looking at the substrate, if we identify it as a strong nucleophile, we would most likely predict SN2 reactions. If we have a weak base and a weak nucleophile, almost always are we going to see E1 and SN1 at about a 50-50%. E1 and SN1, we're almost always going to see them with each other. A lot of times people say that heat will guide elimination reactions, it will guide E1 reactions, but that's not always the case. So I think it's safer to say E1, SN1 happen at the same rate, at the same time. They're always competing with each other. If we have weak bases and weak nucleophiles, they're going to go first order because of that carbocation formation. A couple of things you want to look at here. The first being its degree. So you want to see how substituted is the carbon that we're looking at. If we have a tertiary carbon or a secondary carbon that can rearrange itself to a tertiary, or something that has a double bond or a benzene and it can distribute its positive charge, that's also going to indicate first order. When we're looking at degree, if we're really stable as a carbocation, so either allylic, benzylic, or tertiary, there's a good chance that we're just spontaneously going to go through our first order reactions. And if we look at our solvents, now you don't really want to base solvents as your sole model for what we're going to do, but it's really helpful. If we're aprotic, which means that we don't have any availability for hydrogen bonding, so we don't see OHs, NHs, we don't basically have an opportunity to form hydrogen bonds, we're going to be aprotic. That's going to be an SN2 reaction. The reason that's going to be SN2 is because if we have hydrogen bonding, that nucleophile might get distracted and not do its backside attack because the nucleophile would rather do hydrogen bonding instead. Now, if it's polar protic, it can either go E2 or anything first order. Let's take these applications and put them into some examples. Let's look at some reactions and apply what we just looked at. Let's look at this first one right here. We have cyclohexane with a methyl group and an iodine group attached. And we have a methyl hydroxide attacking it. The first thing we want to do is look at the attacker. Look at the nucleophile. We have methyl, which is CH3, with an OH. So you want to see if this is ionic. If this is ionic, that means they're going to break up when they go into the solvent, and then we're going to get a negative charge. We know we're most likely going to be second order at that point. Methyl hydroxide is not ionic, so it's going to stay as CH3OH. We don't have any charges here. That leads us to think that this is going to be a weak acid, weak base. If we were to also look, what's the conjugate acid going to look like? CH3OH2, and then the oxygen is going to end up being a plus. That's less stable than when it is now. This is going to be a weak acid and a weak base. That leads me to go SN1, E1. But what are some other indicators? If I look at the carbon in question that has the leaving group, it is tertiary. It has 2 carbon attachments from the cyclic ring, and then it has 1 from the methyl group. So when the iodine leaves, it'll form a tertiary carbocation, which is very stable. That's also going to lead me to think that we're going to have a first order mechanism here. If we want to draw out our predicted products, we're going to draw our cyclic ring. One of them is going to be the SN1, which is going to be the oxygen and our methyl group because we'll have deprotonation, because the oxygen will have the plus charge. And then we'll have our E1 product. Here's the thing. We can have 2 products here. We can either have, since this is our carbocation here, we can either have this product or this product. So either on the methyl group or the double bonds inside the ring. Well, which one's the correct one for this case? If you want a complete breakdown of how I get these answers, all the individual videos for SN2, E2, SN1, and E1 are all linked in the description. That'll go more in depth on how I'm getting these answers. Here, we have to figure out, do we want the Zaitsev product or the Hofmann product? Well, the Zaitsev rule says that, especially in our E1 reactions, we're always going to get the double bond on the more substituted carbon. The only time we won't is if we have a bulky base. Typically, when we see that, we'll be going E2 anyway. This is the correct elimination product. We'll still see the Hofmann product, it'll just be in a much, much less quantity. So let's look at number 2 right down below. We have another cyclic ring with an ethyl group coming off and the bromines on that ethyl group. So here we're reacting with sodium cyanide. This is ionic. We're going to have our Na plus and our Cn minus. Additionally, if you look at our solvent, it's DMSO, dimethyl sulfoxide. This is polar aprotic. We know polar aprotic favors SN2. We also know that if we have a strong base, strong nucleophile, we're going to go second order. So it's looking promising that we're going to have a SN2 reaction, but let's confirm it even further. We know our nucleophile is going to be cyanide, that has the negative charge, but is it a strong base, strong nucleophile, both? Let's figure it out. If we look here, this is what we're working with, and then we can have either the negative charge on the carbon or on the nitrogen. So it does show resonance, it's more stable, that means it's less willing to be a nucleophile, but that doesn't fully eliminate it from being a nucleophile, because there were 3 things that we wanted to look for in our nucleophile. One of them was the localization of electrons, so there is resonance that makes it a little weaker, but one of them was steric hindrance. Cyanide is very small. It's only 2 atoms and they're not very large, and they're connected by the triple bond. So that's promising for it being a good nucleophile. The last thing on our list was the charge. It has a negative charge, it wants to share, that also indicates that it's strong. So it checks 2 of the 3 boxes in our list. This is going to be a relatively good nucleophile. This is going to go SN2. And our product here is going to be our cyclic ring with our cyanide attachment. Let's look at the problem on the top right. We have a 2-bromobutane group, and it's reacting with tert butoxide. If you remember, tert butoxide was one of the classic examples, one of the examples I gave for a super bulky base. But let's confirm that anyway. Tert butoxide is an O- connected to a carbon that has 3 methyl groups attached to it. This is very bulky. Is it a strong nucleophile? Well, it has a negative charge, so that's good. The crowding, does it have steric hindrance? Yes, it has a lot. That's going to tell me this is a very weak nucleophile. But let's look at where those electrons are localized. Well, they're localized just on the oxygen. There's no delocalization through resonance. This checks 1 of the 3 boxes. It's going to be a weak nucleophile. Is it going to be a strong base though? If it's a weak base, we might go first order. If we look at the conjugate acid of tert butoxide, it's tert butanol. The O- ends up becoming an alcohol group, which is neutral. And this neutral molecule is much more stable than having a negative charge. So this is going to be a strong base, but a weak nucleophile. We're going to go second order E2 reaction. Our product will either be a double bond on the first carbon or a double bond between the second and the third carbon. Which one will it be here? If you know E2 reactions, or you saw my video on E2 reactions, you'll know that if we have bulky bases, our Hofmann product is going to be our major product. Hofmann product is the least substituted. That's the easiest for a bulky base to get. So that means our Hofmann product is the major product in this case. Let's look at one more example on the bottom right. So now we have another cyclohexane with 2 methyl groups and a bromine group. And we are reacting it with sodium hydroxide in acetone as a solvent. Acetone is polar aprotic. So that's something to note, but again, we can't use that as our only measure. Let's start with the nucleophile. It's going to be our hydroxide here because this is ionic. So hydroxide, if we think, is this a strong base? It has a negative charge, and if we think about the conjugate acid, which is water, water would be much more stable than our hydroxide now. It will be a strong base. That favors E2. Let's see if it's a strong nucleophile. Does it have a negative charge? Yeah, that means it wants to share its electrons. What is its size? Is there steric hindrance? There's not. It's very small, so that means it's also a strong nucleophile. Is there any delocalization of electrons? No. So this checks all 3 boxes for nucleophile and passes our conjugate acid test for being a strong base. That means hydroxide is a strong acid and a strong base. Well, let's look at our substrate now. We have a bromine and a methyl on the same carbon. If our OH tries to come in and do a backside attack, can it do it? We're going to have a tertiary carbon here. If we ignore bromine, we have a 1-methyl. The carbon's attached to one carbon here. Carbon's attached to another carbon here. So SN2 cannot undergo if we have a tertiary alkyl halide. That means even though we have a polar aprotic solvent, and even though we have a strong nucleophile, we also have a strong base. That means E2 is on the table. The fact that we have a tertiary alkyl halide tells us that we cannot do SN2. We have to go E2. Our product here will be our cyclohexane with our methyl still. And then we have a couple options on where our double bond can go. It can either go here, or if I were to draw this again, it can go here on that lone methyl, or it can go here. Which one will be the major product? If our alkyl halide or our base don't have a lot of steric hindrance, we're going to go for the Zaitsev product. We're going to go for the product that has the most substituted carbons in the carbon-carbon double bond. That's going to be the first one that we drew right here. The carbon that's on the right has this methyl group and another carbon. It has 2 substitutions. The other one also has 2 substitutions. The one on the right, well, this one has 2 substitutions, but this one has no substitutions. And then if we look at the one on the bottom, we have this carbon only has 1 substitution, and this carbon has 2 substitutions. The one that's tetra substituted altogether, that's going to be our major product. It's our Zaitsev product. If this video did help you determine between SN2, E2, SN1, and E1, please make sure to leave a like and subscribe, as it'll really help the channel. If you want a more specific breakdown on any of these 4 reaction mechanisms, I will leave a link to all 4 of their individual videos in the description below. Thank you for watching.